Okay, so
Yeah, we need to wait until it starts, and we need to actually turn the sound on before. Yes, no, no, no. It's a good thing to do. I did it before.
okay, please welcome Hannes, and you're going to talk about Mirage OS.
Yes,
Cool, thank you.
thank you. Yeah, my name is Hannes, and I talked on the last two Bornhacks already over MirageOS. So this time I will focus more about the stuff we did within the last year. But I will also give first a brief introduction to MirageOS, then my current situation or so, and then what I find noteworthy over the last year. And this is an old slide. This is mainly 3 points. It's Connex, which is repository signing, then a DNS stack, and then a CalDAV project I've been working on over the last years. So what is MirageOS? It is, well, I like this visualization of a stack, what we currently use as a service. So we use applications. So the application is just on top on top of here, and the application contains of some configuration files distributed in your file system somewhere, then an application binary, and the binary is likely a dynamically linked interpreted Python script or something like that. So you also have a language runtime, like the Python language runtime or the C language runtime, so the libc and so on. And that's only the stuff you see or you face on your application side, what you are actually interested in. But then you also have this operating system, which is usually a fully fledged system with user processes, kernel threads, and file system, and a network stack. And this is all implemented in the kernel and is very general purpose and very much. And then you execute basically that application within that operating system on top of a hypervisor. So the hypervisor is another operating system which manages all these virtual machines. So you have a lot of layers of abstraction and a lot of layers of code which are there. And so debugging all of that stuff is complex because you need to go down, drill down some layers every now and then you have to get to know to the file system kernel code or so in order to debug a concrete problem. So how that application is, basically the top of the iceberg is basically the code you actually care about, the code you developed, the stuff you do. But then you have the bottom of the iceberg, which you can't see, and that is the code that the operating system insists you to use and insists you need. And whenever there are security issues in an application or so, or security issues in a whole program, you have to take into consideration that also the code you don't care about, but which is part of the operating system, might be vulnerable. So any security issue also in the operating system may affect your application or your deployment. So what is MirageOS? MirageOS is a library operating system where each of these systems is tailored exactly for that purpose. So only a single purpose virtual machine. It mostly or mainly targets hypervisor technology as well, but instead of, but we reduce the trusted code base, so we reduce the attack surface drastically, and we also reduce the number of attack vectors. So the different ways you can get into the system are smaller because we use a high-level programming language. And we reduce the trusted code base or the attack surface by reducing the code size. So instead of having everything in there, you have a very single-purpose operating system which solves exactly one problem. So compared to a conventional stack on the left, MirageOS on the right only contains a runtime system and the application code itself. So you don't have the general purpose operating system and all of that kernel services, because usually you don't need it if you're running a single service. And a single service might now be a DNS resolver or something like that. So now I wanted to briefly give you a demonstration of how such a Mirage system may work. And in order to do that, I prepared a very simple application. I hope you can see that. That is as huge as I can get. So what is a MirageOS? What is a simple MirageOS unikernel? Well, it is obviously a Hello World application, which at the moment only says hello. But it does though, so it defines here a function. That is a function. It's called start, so it's the main function of an application. And it says, oh yeah, well, here's a recursive loop, and please execute the loop 4 times. That is done here. And the loop function goes around and prints hello. This is done via this logs call. And then sleeps for a second, and then calls itself with a predecessor. So it will execute itself 4 times. This is the whole operating system I want to show you. It's, only 10 lines of code. With MirageOS, we now can target different backends with that thing. And we also need to take care about some more compile time dependencies and some marshalling. So we need to configure the operating system as well. And the configuration in this case is very simple. We say at the top level that we want to register a virtual machine called hello, and it should just execute main with some default time source. So we have the time source and other resources from the operating system explicit instead of them being implicit. So if you want to use a random number generator, you have to say so. If you want to use a file system, you have to say so, and you have to deal with that complexity already in your programming language. So there's no big Unix sockets API or POSIX API, which is there already, but you start with nothing. So there's nothing there. And if you want to use any resource, any external resource, also like the console or the network interface, you have to configure that explicitly. Now, what does this register here do? It says main, and main is just a reference to unikernel.hello. That is the stuff we saw here above. It's the module hello in the file unikernel. And it gets its signature is basically it gets passed a time, so a time source, and it will return a job. So the start here also actually gets a time, which is here of a specific type. So it's a module which has a specific API, and that is defined here in the Mirage time LWT. Okay, now we have those two files, and now we have a command line utility which is called Mirage. And now we can run Mirage configure. Mirage configure will generate some code, and afterwards we can say make, which will build the code. And now we end up with a binary called hello, which is a symlink to that file, which is 64 bits dynamically linked executable, which in this case depends on the threading library and the libm and the libc. So it's a normal Unix executable. I can execute it on Unix, and I see the output I would expect. So it says 4 times hello to me. So that is the basic thing. So it's only a Unix executable, which is dynamically linked against some more system libraries. Plus, it contains some OCaml code, which is compiled to native code and then statically linked. So all the OCaml code is directly in there. The size of this unikernel, so this is a Hello World example, and the size is at the moment 11 megabyte, which is not very great. We can strip it; it will become a bit smaller. But there's also a OCaml. OCaml itself is a very active language, so it's not yet finished. And there are some opportunities to reduce the code size, and we can get it actually down to 700 kilobytes or so. But as an alternative, I can say Mirage configure -t for targets, and then I say UKVM. UKVM is some backend which initially targeted only KVM on Linux, which is a hypervisor technology, but nowadays is the same piece of software is able to target other platforms, other hypervisors as well. In this case, I'm running here a FreeBSD system, so it targets a FreeBSD hypervisor called Beehive. And Beehive is similar to KVM type 2 hypervisor, so it requires you to use the virtualization bits of your CPU. And it doesn't do the emulation, so it requires EPT for the extended page tables and the VTD and VTX. Only VTX. And now I can execute that. Now executing a KVM virtual machine, usually on Linux, requires you to run QEMU to emulate all the system resources, so the network interfaces and the console and the VGA and whatever. We thought this is a bit complex and a bit too much code. So together with some people from IBM Research, there's a project called Solo 5, which is a minimal thing which can run in the host system in order to manage virtual machines. This is called UKVM bin at the moment. And UKVM bin gets as an argument the Mirage configure and make now produce a binary called hello.ukvm, which is a completely statically linked ELF executable. So there's no dynamic linking anymore involved. And it doesn't run as a Unix binary because it's not a Unix binary. It's an ELF binary, but it requires to be run inside of such a Solo 5 system. And so now I can execute that, what I see here, what we see here is the same output. So again, application said hello 4 times. But before that, we see the boot screen of Solo 5. So Solo 5 was just initialized with 500 megas of memory. We can actually reduce that by giving it only, let's say, 60 megabytes of memory. 16 is not enough. Yeah, 24 is enough. Yet currently still not finished, but we can get away with less memory. We just need to tweak also the OCaml runtime environment, which we haven't done so. So that is what we can do with Mirage. So we have the very same code base, and on the one side, we can execute it as a Unix binary. On the other side, we can execute it as a virtual machine. And this works not only with Hello World applications, but also with other applications which use network connections and block devices and so on. So what is supported inside of Mirage these days in terms of protocols is this is likely incomplete, but this is at least a first show what is there. And now the question is why it is difficult to implement a new protocol for MirageOS or for OCaml. And the reason is because we actually write that all from scratch, because we write it in OCaml, so we don't reuse any systems code written in C. And yeah, developing protocols in OCaml, like developing protocols in other high-level languages, is quite some effort. But yeah, we have a TCP/IP stack. We have an HTTP implementation, server implementation. Actually, 2 server implementations. Then we have a DHCP server. We have a student in Cambridge also worked on a BGP implementation. I worked, as already outlined, on a DNS implementation and also some Let's Encrypt stuff. Then we have a partial working SSH server implementation. We have a TLS implementation, which is now 4 years old, I think. It still lags TLS 1.3, which was just finalized the other day, but yeah, I have some branches for that. Then we have a Git implementation, which is pretty complete, so we can pull and push to Git repositories to the remote side, but we can also use a Git repository inside of our virtual machine without having it on a block device. So we can have a Git clone and a Git checkout, which is purely done in memory. So you just, yeah, you don't need to have a lot of persistent storage for a lot of services, in my opinion. Then we have a partially working OpenPGP implementation, which I think Joe will talk about on Tuesday a bit more. And yeah, we have some monitoring and logging support for syslog and Prometheus and InfluxDB and SNMP. What are the targets? So what are the targeted platforms? And initially it started out as a Xen project, MirageOS. So the initial target was Xen. It was initially developed by some of the people who were also part of the Xen team. Then, as I mentioned, we switched over to also be able to run on KVM. Nowadays, we also can run on Beehive, on FreeBSD, and even on VMM from the OpenBSD project. Another hypervisor we can run on is Muin separation kernel, which is, in my opinion, very interesting because it is removing a lot of dynamic resource allocation away, and also does it only statically resource allocation. And it is developed in Spark Ada, so in a language which is also not prone to various spatial and temporal memory safety issues. Backends in the name of system, so hardware processors, is AMD 64, which is deployed everywhere. So the x86 64-bit. Then we also target ARM, both in 32 and in 64-bit for Xen in 32 and for KVM in 64-bit. And then we can also target the so-called cloud, like Google Compute Engine and Amazon and Telecom's cloud, maybe. So what happened inside of the OCaml and MirageOS ecosystem within the last year? It is, I think, a major change is that we reworked the build system, and we now adapted to a high percentage new build system, which is actually easier to use than the others, especially for newcomers, because you don't have to deal around, you don't have to fuzz around with 3 different file types and so on. And it does not depend on the old tools, so to say. So we can hopefully in the future get rid of some layers of abstraction and layers of names which are no longer required. Then OPAM is the OCaml package manager. That will finally soon see its second major release, and that is great because there has been work over the last 3 years on OPAM 2, and it is finally there. So there's currently a 4th release candidate, and it will be released as the final in September. We also worked on the documentation generation front, so that is more the OCaml community which worked on that, which generates API documentation, and they even embedded it to have a workflow to be able to write a book. So they write the book in some style, some markdown style thing, but include some code examples, and these code examples can be extracted and can be compiled then. So to ensure that while you write your book, your code example actually working. And I think that's great, and I hope that we will be able to adapt that same library for writing some text and some how-tos about MirageOS. Then also within the last year, OCaml did some major releases, and one was 406, where strings are no longer mutable. They used to be mutable since the beginning, and then they switched over and made strings immutable. And now finally, by default, all the strings are immutable. Obviously, that's a breaking change for old code, which hasn't been maintained for quite some time. And we also needed to adapt quite some code to be safe with immutable strings. Since the beginning of this year, I'm working on at a non-profit company called the Center for the Cultivation of Technology in Germany, and I'm working there with a project called Robur, which goal is to develop robust digital infrastructure. And our real goal is to enable more people to run their own digital infrastructure and be able to take back control over their data. We try to collect money via donations or commercial contracts and or public funding. And everything we develop is open source, and we are obviously still looking for donations and also for contracts. Now for the first big project I've been working on is Connects, which is repository signing. I've been working on that since nearly 4 years, I think, and this is now the 5th prototype implementation and the 5th design after I met with one of the professors who designed the base system, which I base the design and the usage on. So it's based on the update framework from Justin Kappos and others. What is the main goal here is to establish trust into community repositories. And community repositories are, for example, a package repository where every author submits their own package. So you don't want to have a single point of trust, or at least I don't want to have a single point of trust, and I also don't want to have to trust the repository server, because that might be compromised at some point. So how does that work? In Connects, each package is maintained by its author or a team of authors. And the author is supposed to sign their package on every release. And signing the package includes the checksum of the tarball of the release, but also the build instructions and the dependencies, like external dependencies to libraries. And then if every package author does that, the only connection we are missing is who's now responsible for which package name, because we have a globally unique namespace of OCaml packages, because we need to formulate those dependencies in there. And this delegation is done by a set of janitors. Janitors are maintaining the repository or the main OPAM repository, and obviously we can have any number of OPAM repositories with any number of packages and any maintainers in there. Yeah, and the goal is if the janitors sign such a delegation to a specific author or to a specific team of authors, then the authors can do with that package whatever they want. I mean, they can draft new releases without the janitors having to do anything, because they already delegated it to a specific author, and the author can just add new releases or adapt fixes, fix up the build instructions, add new dependencies, add new version constraints, and so on. How does that in reality works? Well, so this single author for a single package is no longer true, because there are lots of packages which are maintained by teams. And an author may have multiple keys. So I may have a key on my laptop and a key on my desktop, and I want to be able to specify, oh, it doesn't matter which key has signed this release. It might also be that I want to require, oh, I have a YubiKey, so an external hardware security module where I store one of the keys, and I want to have that HSM need to sign the release and also one of my other keys. That led also in so in the update framework, to the introduction of quorum signatures, which basically means that you can specify, oh, I want to have 3 signatures out of the list of valid people or valid authors. So if I require 3 signatures out of janitor A to janitor E, some delegation or any delegation is only valid if at least 3 of them have signed that delegation. It's also true in the real OPAM repository, like from running it over time, and we have just a Git repository, which we are hosting on GitHub at the moment, and where any package authors submit their packages. It turns out that authors are not responsive enough for big breaking changes. So if someone releases their library and that is depended on by a lot of other libraries, and now he releases a new version of that, which breaks the API, but he didn't tell that up front, then we may have to fix up a lot of other packages to introduce a new version bound, so a new upper version bound that they are not compatible with the new release. Doing that by the individual authors would be the right thing to do, but sometimes authors are on vacation or so, and we don't really want to wait for 3 weeks or for a month in order to just put through a new release of a package. That's why the janitors, so the janitors are those people where all the trust is initially delegated to. They are able to also approve checksums of these new packages or of these adjusted packages. Yeah, and this also means to require quorum here means also there's not a single key which is able to compromise the entire system. So if the key from janitor B gets compromised, or if I manage to steal it, I cannot introduce new packages or make something valid, because I need at least 3 keys out of those 5 in order to do something which is thread valid. Yeah, another thing in reality is keys get compromised. So if I design a system which relies on public keys and so on, I better think about how to mitigate compromise and how to deal with it. And there are various ways to deal with that. So if here janitor A, for example, loses their key, then 3 out of the other 4 janitors can still say, oh yeah, well, that's fine, janitor A is no longer part of our group, or they can add janitor A with a new key. So they can actually roll that over and they can expand and shrink their own team. Yeah, what is the progress of Connex? Well, there's, as I mentioned, there's now a new prototype implementation with the revised design, which I revised together with one of the update framework people. That is available now. It interoperates also with OPAM2. So obviously this project itself needs to integrate somehow with the package manager, because package manager, I would like to tell the package manager to only install valid packages. And the only small area where it needs to interoperate with OPAM itself is during repository update. So how a repository update nowadays works in OPAM2, it fetches the diff, or it fetches the new repository, then it makes a diff, then it passes that information or that file to Connex, and Connex is just a Unix binary, or Connex verify is just a Unix binary which says yes or no, so which returns 0 or 1. And OPAM2 only if it successfully gets a successful return code from Connex verify will continue to adapt this updated repository. And I prepared some bits and pieces. One is so OPAM2 is, as I said, currently in release candidate state. But once that's out, we can just add repositories with OPAM repository add. And now I have a Connex test, and I will use a local repository here. Then I say the quorum for the root, so for the main trust anchor, is 1, and the public key, which is able to sign something, is having this SHA-256 checksum. So in this example, it's only a single key. It's not the optimal solution, because I would like to specify here 3 out of whatever. But this is just for test. Now that failed because it already had a Connex test. Yeah, it says invalid repository signature update aborted. So something went wrong here in the test repository here itself. I can also say Connex verify so manually, it says uncaught exception. Yeah, we'll get back to that later. So what is inside of the repository is, apart from the janitors, it's first a file called root, which specifies what are the janitors. So I have a 2-level setup here, and next to the janitors, it's also can specify a snapshot and a timestamp bot in order to preserve liveness guarantees. And specify means here it specifies the name, and then on the right-hand side an expression. In this case, it is an expression of quorum of 2 of the janitor 1 and the janitor 2 with their specific public key hashes, and then the janitor 3. So there are 3 different janitors with these public key hashes, where 2 of them need to sign any delegation in order to make that delegation valid. What else is in here is name. Well, the name is root. And then a list of public keys, which are the root public keys. And this is the RSA. This is just a RSA key, which checksum I then specify on command line. What else is specified here is where are the keys and where is the data I want to verify or I want to have. And the list of signatures, and this in this case it's only a single signature by the key named root A, and the signature is in here. Then each of the janitors have their own file where they also have their own signature, and in their file they specify their targets, so they can specify delegations and targets. And the targets are the actual data files. So they consist of a file name. So the file name foo 1.0/opam has the size 0x1ff, and its digest should be this checksum. And then another file name, which is bus/opam, should have that digest. Now, this is only a single janitor, and the single janitor then also has their public key in here, and also has here delegations, and it delegates the path foobar to the user foobar. So the user foobar is here, and the user foobar can only specify targets which are below the directory foobar. For example, test.txt. And the delegation to foobar here also means that foobar is the only author responsible for that subdirectory. So there doesn't need to be a quorum, but only this single foobar. But inside of the root file, I had an expression that I need 2 out of the 3 janitors to make something true. This is also the reason why there are multiple janitors here, and the janitor 2 has a different set of targets files and no delegations in this case. And the third janitor also has a different set of files, and then as well the delegation to foobar. So two of them have the delegation to foobar, and that makes the delegation only valid. If only a single janitor says something, this target or delegation is not treated as valid. So what else? I also wanted to talk a bit about microDNS, which is an opinionated DNS server and resolver. DNS itself is a protocol used all over in the internet. It is decentralized and delegated key value store, where the root authority is at IANA and has 13 root servers, and they delegate country domains and TLDs to other registrars, and they delegate then further subdomains to other people and name services. The main purpose of DNS is to resolve domain names to IP addresses. That is that is why it is used, or for what it is used most on the internet, but it does contain also lots of other fun stuff. So you don't have to use domain names, and you don't have to use IP addresses, but you can just store any key value data for which you are authoritative. The project itself started actually out because I wanted to implement a DNS resolver, a recursive resolver. So my motivation was, I really want to understand what are the difficulties in resolving a domain name. Now, obviously, I can always go to Google's name server and ask Google's name server, what is the IP address for google.com or for facebook.com or so. But I wanted to actually do it how it is defined in the RFCs. So instead of going to a caching resolver, I want to go to the name servers, which are run by IANA and by the other companies, and just go through this whole network to find out which name server I have to ask for what. So the motivation was a recursive resolver. I figured out pretty quickly that I want to also be able to configure that recursive resolver, like blacklisting advertisement networks or having local overrides. So if I own my own domain, I maybe want to have a different name server responsible for me as an internal user of that domain. So my development network and so on does not need to be public, but on my laptop, I want to be able to use DNS for resolving also my internal names. And then I figured out that actually DNS has a lot of configuration information already in band, and the protocol itself specifies zone files, which is a format for serializing domain name data and put it into the server. But it also specifies dynamic updates of such zones. And it also specifies authentication, so authorization of packages, of DNS frames. This all let me think, oh yeah, I can just implement a DNS server and then use the DNS server, which has dynamic updates and so on, as a front end or as a configuration front end for my recursive resolver. This also means I don't need any persistent state. Just delegate that this is not my problem here right now. I just start with a clean state and get as a boot parameter maybe the secret for the HMAC. And then you can do dynamic updates or dynamic configuration changes of the resolver. Yeah, this led me to actually implement the authoritative server in DNS or for DNS, which implements zone files, so it can pass zone files. It can receive dynamic updates, and obviously if I can receive any dynamic updates, that's not much use because I want to have some authentication for that. And for authentication, DNS specifies TSIG, which are HMAC secrets. So you have shared secrets, which you can do. Another method of authentication, which I haven't implemented yet, but I'm going to implement soon, is to just use DNS over TLS and require TLS client certificates. The server itself does not need any persistent states. So no persistent block device, or so the DNS server is just another virtual machine image which you start and which has its initial data, like the HMAC secret, and afterwards you can fill it dynamically with more data. So if I look into my examples, I will briefly go to a primary implementation. This again is a unikernel, so I have a configuration which is now a bit more complex because it already includes some IP information, because here I'm using actually an IP stack. Then I have some more packages as dependencies, and then the unikernel itself now says, oh yeah, here is actually my data. My data contains of a start of authorities of some entries and some A entries, and also some secret HMAC secrets, so some secret keys, which are all in the end fed to the primary name server, which then does listen on the network stack. Now I can say Mirage configure -t ukvm and make. And I end up with the primary.ukvm, which is another unikernel, which I can now start. So I now have to pass the the UKVM bin, so the host system process the information which network device the unicorn should use. I use tab 1, and then I pass the virtual machine image, and now also increase the log level. So now I have a server running on the IP address 10.0.42.2 on my local machine, which is all connected to a local bridge. And I can now dig any, so I can request information about the zone I configured here. The zone is named Mirage. Can also try to initiate a zone transfer, which doesn't work because it doesn't respond. It says transfer failed because zone transfers here require a key. So if I give this dig key with the zone transfer, I actually get the whole zone out here. So that's basically how I run at the moment my name services. They are just those Mirage unikernels, which don't have access to any block device, so they can actually not write any data. They cannot record IP addresses and so on. And they don't need to. Another step, once I had this DNS server, is that I'm continuously running into this issue of Let's Encrypt certificates needing renewal. And Let's Encrypt is a very nice, specifies a very nice protocol where you can prove your ownership of a domain via DNS as well. And now that I have a DNS server written in OCaml, which does dynamic updates and so on, I thought, oh yeah, let's integrate the Let's Encrypt library, which a friend of mine, Maker, has implemented in OCaml, and just use that. And now I end up with having a unikernel, which is a DNS server, and which is also able to deal with the Let's Encrypt ACME protocol and provision certificates, or provision certificate signing requests to certificates. And how I set that up, because I don't want to have all of that inside of the primary name server, I just have a secondary name server which deals with the Let's Encrypt updates. And I store the Let's Encrypt certificates and the Let's Encrypt certificate signing request also in DNS, because it is a key value store after all. So let me just store my signing requests and my certificates in there. All this storing is obviously protected or authenticated by the HMAC secrets, which is only basically a signature, but there's no encryption involved. But there doesn't need to be any encryption involved because it's not private data. There's just a certificate signing request and the certificate. And now this Let's Encrypt DNS secondary server goes along and waits for zone updates. And whenever it receives a zone update, it checks whether all certificate signing requests have matching certificates, where matching is defined as, oh, they have the same, they use the same public key, so the requester can actually use it, and the certificate is still inside of the validity range. So since Let's Encrypt is only valid for 90 days, it will renew then after 89 days, I think, at the moment, or 88 days. Okay. Now, still, I haven't had any persistency, so I don't store any data at the moment on disk. It's all only in the memory. You can get away with that by running multiple DNS services and yeah, just have a failover from primary to secondary if the primary is down, and so on. Okay, I have to hurry up. In UDNS, I also have persistency using Git, because as I mentioned in OCaml, or in MirageOS, we have a Git implementation. Now I can just push zone updates also to a Git repository and commit that. And the primary can retrieve Git information. So can clone a Git repository and use the zone file inside of the Git repository as a as its zone file. So wrap up, I have a server and resolver. I interoperate with other servers. I don't have any custom configuration language because I thought DNS protocol is expressive enough. I have this hidden secondary for persistency and Let's Encrypt. Let me briefly talk about CalDAV. CalDAV is a protocol used by calendars to sync calendars. This is a project which we got funded by a prototype fund, which is a very nice funding program. CalDAV itself is based on WebDAV, which is the data and versioning in the web. So it does some authentication using HTTP authentication, does XML requests, which are specific for retrieving and uploading files. We worked on that since April this year, and it's still work in progress, but it's coming along well. And it is just impressive how complicated such a CalDAV protocol is. On the one side, you have HTTP and embedded XML requests. On the other side, you have the iCalendar file format, which is more like a RFC 822 key value thing, but then they thought keys and values are not enough, so we need multi-line values, and then also we need parameter keys and values for each key. So it actually turns out to be pretty complex to parse and to operate on it. Also the recurrence rule, so you can define recurrent events like a weekly event, but not in the 50th week, but only in the 48th week or something like that. That's all I prepared. So what is MirageOS? It's an operating system engineered using a very radical approach by just getting rid of everything we have right now and redeveloping it inside of a fresh, high-level language. It avoids a lot of root causes of common flaws, like memory safety issues. It has a very small trust computing base and a reasonable performance. I didn't show any numbers, but from our work on TLS, it turns out we were up to 85% the speed of OpenSSL. Yeah, and let me thank all the contributors to MirageOS, which is now in the, 50 people or so. And I'm also organizing every 6 months the hack retreat for the MirageOS system. If you're interested in that, the next one is in early October. It's a week in Marrakesh, and yeah, you're welcome to join us there. That's all I prepared. Do you have? I think we have some time for questions, or? Okay.
So, any questions?
Thank you for the nice talk. The Connex, did I miss it, or is there some like proof of publication mechanism? So like if you're a developer and I've compromised one key of one developer who's the only developer of their package, and I control your Wi-Fi, can I do a targeted malicious software update and get away with it, or is there some mechanism to?
There's a mechanism called the snapshot bots, which receives the repository, checks all the signatures, and makes a new signatures over the global view of the repository. But if you compromise the repository update mechanism, you can, thanks to the snapshot bot and the timestamp bot, which just does every 5 minutes a timestamp and a signature on the whole repository. You can check for liveness properties, like that you don't get that the attacker can't freeze you to an existing bad repository. Now, if I compromise an author key and the author doesn't, as long as the author doesn't detect that, I can publish new packages under their name. That will then hopefully be discovered by the repository maintainers at some point, hopefully earlier, and they can then revoke the public key or the delegation to the public key.
But what if it's a targeted thing where they don't I guess I'm more worried about if it's a targeted attack where the attacker does not actually put the new package in the public repository for everybody, but instead just presents it to their victim. So they, you know, you're a developer, you're on some Wi-Fi, and the attacker is physically near you and has compromised one author key. Is there a way to be sure that the package I'm installing right now is the same package everybody else would be installing?
Yes, thanks to the snapshot bot, because you as a client, you first check the signature of the snapshot bot, and that signed all of the authors. So the attacker would first need to inject that new package into the snapshot bot.
Right.
And
So
the
are there
snapshot,
multiple snapshot bots, or is that?
yes,
Okay.
you can have, you can also have similar to the other quorum signatures, you can specify, oh, I want to have 3 out of those 10 snapshot bots, which are then hopefully run by different organizations. And they all need to agree on the state of the repository.
Great, thank you.
You're welcome.
Thanks a lot. It was
Thanks.
very nice.